here is Logic for Computer Science, Classical and Non-Classical, a textbook which I use for my logic courses, Springer 2019, and I'm the author. So, Chapter 3. And here are our Chapter 3 slides. The remark is I split those slides into sets. They are split thematically. It's a big chapter, and I do the same for all other chapters. And so when you study, it helps you to concentrate on parts to study one after the other, or whatever parts you want to do. So slide set 1, 2 parts, because again, thematically, it focuses on what it is. We'll talk about formal propositional languages, nice introduction, and then we'll have the formal definition. And then we talk about semantics, and we define general extensional semantics M, and as the part 4, slide set 3, we do the classical semantics as an example of extensional semantics M, and then we study a little bit of classical semantics. We'll go pretty fast through it because you assume that everybody knows a lot about it. But so this is part 5 and 6, and then again, this is still classical semantics, classical tautologies, logical equivalences, definability of connectives. These are like the minimum you have to know about the structure of classical propositional logic. And then we go into, as example of non-classical, of extensional non-classical semantics, with part 9. We will do many-valued semantics, Łukasiewicz, hating Clini, will go as others examples. And then in last part, we will show how all which we did for classical part, classical tautology, how you generalize it to any M extensional semantics. So this is a nice generalization, and you see how, and we'll talk equivalence of languages, everything which we understand and know for classical semantics, we'll do it for any extensional semantics. So, propositional languages. First, we define now general notion of propositional language. So, propositional, we assume certain things. And we want to cover not only classical languages for classical logic, but also for variety of non-classical logic. So that's why we define a general notion of propositional language. And first, we assume certain things, that each of those languages, so all propositional languages, have infinitely many variables. And this is how we will write. We write A, B, C, small a, B, C, P, Q, X, Z, with indices if we don't run out of letters of alphabet. But usually I use A, B, C, D. We use them as symbols which denote for propositional variables. And of course, all propositional languages share the general way we define the set of their formulas. But really, because they share the way you define formulas, what distinguishes one language from propositional language from the other is the set of connectives. That's why we write L con to define for the language L. If we already have fixed set of connectives, we just write L and we'll say propositional language L. For example, this language means that the language has only one propositional connective negation. We call it negation. That means that that language two, one argument connective negation and implication and so on. And thing to remember, formal languages deals with symbols only. That's why they are called symbolic languages. So, of course, this is only symbols, but of course symbols for connectives and later all other symbols have intuitive meaning. So semantics provides a formal meaning of the connectives and is defined in the next step separately. And of course, one language can have many semantics. You will see this language can be a language for intuitionistic logic, many valuate logics, etc. So semantics, this language can have many semantics, and we'll discuss it later. Of course, also we have also the fact that several languages can share the same semantics. For example, due to functional dependency of logical connectives, all these languages are equivalent, and we will define formally what does it mean for language to be equivalent under classical semantics. And we'll define that. That's why we will define formally what does it mean equivalency of languages. So we can say that all these languages are the languages of classical propositional logic, and we will each time say, I use this language or that, and then we will define the relationship between them. So, and of course, just to remind you that propositional connectives have well-established names and the way we read them. The fact that we read "and," it doesn't mean that semantics for "and." So, and we use the names like negation, conjunction, disjunction, implication. That connective is called alternative negation, and it reads not both N and B. This arrow down is called joint negation and reads neither A nor B. Modal connectives, we have also modal connectives, which are connectives of possibility and necessity. So it means that we use certain symbols. So for example, standard symbol is a box for necessity and diamond for possibility. And we say box A, we say possible A. Also, we use other symbols, which is C and I for modal connective. And so for a reason I will explain later, but you read them in exactly the same. This is C, you read possible that A, and this diamond, you read it is, C and diamond reads in the same way that it is possible that A. So, and we do, the symbols C and I are used for the topological meaning, and we will go to modal logics. I will explain you how, why, and what. So, modal logic extend classical logic. It means that not only they have classical connectives, but all classical connectives semantically, they behave as classical logic. And you have many languages for modal logics. For example, this is I use C and I, here use, these are different languages because I use different symbols. Knowledge logics extend also classical logic by adding, for example, new argument of knowledge. For example, I can add a connective K, where formula KA reads, it is known that A is known, and then I have a knowledge where here K denotes one element, one argument connective, which is knowledge connective. Autoepistemic logic also extend classical logic by adding a new belief connective, B, for example. Often, because belief B, so you use, but you can use any other symbol. And formula BA reads, it is believed that A, and here you have a language which has this connective. Temporal logics, I am listing all this computer science logic, temporal logic, that's basic logic for program, and is still being developed by computer scientists. The same for belief, knowledge, and other epistemic logics. These are all logic developed by computer scientists. So again, temporal logic, also extend classical, and again you can use F, P, G, H as symbols for FA reads A is true in some future, F for future time, P for the past time, G for future, true in all future times. So G is general future times, and H always true in the past, and so on. So there's many different temporal logic use that type of connectives. Also, it is possible, all examples I gave, the connective were 1 or 2 argument. It's possible to have connectives with more than 1 or 2 argument, but we don't include them in our investigation. And now you have formal definition. Propositional language is a pair, A and F, where A is an alphabet, F is the set of formulas. Alphabet is variables, connective, and parentheses. They are non-parenthesis languages, but we use parentheses. So you do declare your alphabet, and then once you have the alphabet, you have set of variables, which I said. You have all, and the way is countably infinite set of propositional variable, non-empty, and countably infinite. And we have what we already said, that L-con means that language L has the set of connectives L. Also, we use the parentheses, which are auxiliary symbols, might be empty, which I already said, but in our case, parentheses is a set which has 2 parentheses. And we assume also that connectives, we have only unary connectives and binary. So the connectives is a set, finite set of 2 disjoint set, C1 and C2. C1 denotes the set of unary and C2 of binary connectives. And now we have set of formulas. What are formulas? Formulas are finite sequences of alphabet. F is a subset of finite sequences. And this is the definition, general definition. If you have a language which have a connectives, what language connectives are unary and binary. So always unary and binary. So the formula, or they are called also well-formed formula, is the smallest set with, you have 3 conditions, recursive condition, that variables are formulas, and they are called atomic formulas. If you have a formula already, and this is a symbol of unary connective, any unary connective, you can have 10, 20 of them. Such expression is called a formula, and when you have 2, you put the binary connective in between, and you put parentheses in between. Let's do an example. This is a general. So let's do a language which has, let's say, negation, P, implication, and disjunction. This is our set of connectives. These are unary, these are binary. What would be the set of formulas of that language? we have the always variables are formulas. And now what it says, if you have already a formula, then unary, for any unary connective, in this case we would have not A is a formula and P A is formula. And 3, if you have two formulas, we have, this is binary connective, then A implies B is formula and A, B is formula. So that is, this A is formula for this is unary connective, and that condition means that if you have binary connective, you always put parentheses and you put binary connective between and you add parentheses. Again, remark that, for example, not A is not a formula, because if you have negation, you don't put parentheses around. Everything is very structured. And of course, it's the smallest, there's the smallest set which satisfies these conditions. So we have, it's called the set of well-formed formulas. And of course, we have alphabet is countably infinite. So the set of all, if you have countably infinite set, the set of all finite sequences is countably infinite. So the set of formulas are countably infinite. So it means that we talk about countably infinite languages. And now we have the notions: main connective, direct subformula. So if you have a formula of this type, you have two formulas. One is of this type. This is example, and the other is of that type, and these are the examples. This is called the main connective. So that is called the main connective. So this negation is the main connective. Here P is the main connective in general. That is main connective in the formula. And A is called direct subformula. And you can see, if you have binary connective, you can see the main connective sits inside, and this is nicely, it says, and now you can see why we put those, because if I want, I have already formula like that, and I want to put negation, I know that I negate how far. Those parentheses tells me what I negate. I negate the whole formula. That's why you have those parentheses. They explain you exactly how far your connective goes. And these are examples. So, and then we define the notion of proper subformula. So any formulas A, B, the formula A is a proper subformula. A is a proper subformula of B if there is a sequence of formulas beginning with A, ending with B, and in which each term is a direct subformula of the next. And of course, the subformula given formula is a proper subformula of A. And here you have a formula. You have two direct. This is main connective. You have two direct subformulas, and this. And now you look at this. You have already this formula. Direct subformula of this is A. Direct subformula of this is this. And now that is already variable, so it's atomic formula. Now you have main connective is B, so the main the direct subformulas of A implies B is AB. So really, here you have A, here from here you have AB, so this is a set. So this is A and B. And this is the end of a process, and that's you know how to find this set of all subformulas of different formula. The next important notion is the degree. The degree of formula is the number of connectives. Very easy. 1, 2, 3, 4. Degree 4. So, and of course, degree is important because a lot of proofs will be carried on the complexity of the formula. It means on the degree of formula in mathematical induction, on the degree of the formula. Now, the book and my lectures have less exercises than the book. I only show some of exercises, so it's good to also to read and to do exercises and examples which are in the book. So, for example, this is a typical type of exercise or problem. You have a set of formulas, determine which elements are which are not well-formed formulas of L, and if formula is a well-formed formula, determine the main connective, very difficult, and if it's not a formula, it means you decide that that is not well-formed formula, something is wrong, then determine correct it and determine. So when you look at this, you can see this is not a well-formed formula because the implication, when you have implication, you need to put parentheses around. So this is not a well-formed formula. And here you have this is okay, this goes to that, and then you can put this, and this is not a formula because that is main connective, and you cannot put, which I wrote it. Oh, here, you see, I already, that if you put around the main connective, you cannot, in our setup, you have, this is not a formula. In our definition of formulas, they are books and they are languages where some authors say, yes, it is a formula. But we didn't say that it is a formula, so it isn't. So that's why you define your language very precisely. And of course, then you correct, etc. So that was important. And then it's more determine degree of formula. First, you have check if this is a formula. Yes, it is main connective. This goes to there. That is correct. So this is, and degree is 1, 2, 3, 4. So it's very, and then you write the subformula. So it's pleasant little exercise. So next important stuff is that how you translate a natural language or mathematical language. For each natural numbers, the implication, then there is a natural number. How you have your English, mathematical English sentence, how you translate it into our propositional formal language. So for example, you have a sentence and translate it into this language or that language. This language has only negation, conjunction, disjunctive implication, and this language has modal connectives because you can see here you have words, natural, not possible. Possible, it is this connective. Possible is this connective, and so on. So I want to go with you to show you that example, how you do it. And this is like typical exercise and typical translation. So now we can have normal sentences and then translate it into formal languages. So when you do the translation, first of all, you look at your language. So you have to identify the connective. You see here, possible. you have possible is this. Not is negation. Can deduce is implication. Not is negation. Possible, you have this. Not a boy, if it is possible, not a boy, that is not necessary, not is negation. You have necessary, and then, so you have necessary becomes disconnective. So now you have, and what are the basic sentences? And that depends on your language. For example, when you look at the structure, if you have this language, the basic sentence, it must be a sentence in a part of your statement which does not contain these connectives. So when you look at this, an is not a boy, so that contains not. So you cannot have this as a basic sentence. What does it mean, an is not a boy? It's not, an is a boy. So you take an is a boy as your basic sentence because it does not connect any connectives. And B denotes this, and now possible and necessary. So these are your connectives, and the sentence, now when you look carefully, would be, this is your whole sentence written in our proper language. But when you have the same language for the same sentence, and you want to use only these connectives, so what happens now, that this possible hides all this because you don't have the connective possible. So your basic statement would be possible that an is not a boy. Not is in our connective, so that would be possible that an is not a boy. Of course, I did it on purpose because you can see that this sentence is the same as that. So that would be your first basic statement. It is possible that an is not a boy. Even you have not inside, but in language which does not have possible, the possible hides what is inside. And again, for the same reason, when you have not, and then you have necessary, an is pretty, so that would be necessary, an is pretty, is your basic statement. So if you want to translate into only this language, and you don't have the symbols for this possible and necessary, you have, the formula would be like that. And there's a lot of examples. And then that is a nice exercise, so I skip you. That, for example, here, the whole, that big sentence would be just, if you have this here, this language, for all natural numbers, you don't have expression for all natural numbers. We'll have to go to predicate language, which would be able to translate the sentence all natural numbers. So if you have only that language, the whole sentence becomes just a variable. So this is an undistinguishable little piece. And B would be that part, so you have only A or not B. So that is just to show you, and there's a lot of examples. The translations are important. And there's more examples. So, extension of semantics. So this is a syntax, how you, what is a propositional language, which language is how we define the formulas, how you translate natural mathematical sentences into a given propositional language. And now we talk about semantics. It means, what does it mean that a formula we somewhere got worth this. Is this formula true or false that depends, because when you have many valued semantics, it can have many values. So what does it mean? You assign some truthfulness or falsehood or degree of falsehood to a given formula. This is called the semantics. And we defined extensional semantics. So extensional semantics, you assign logical value assigned to formula depends only on connectives. Let's put it like that. So it means that logical value of formula depends only how you depends only on logical value of parts of of connectives, how you build the formulas. So for a given propositional language with set of connectives, the symbols have only intuitive meaning. So the formal assignment of logical value to those connectives is called the semantics of the language. And also that there is one thing, and the second is we single out special formulas which are called of the language, which are called tautologies. And intuitively, tautologies are formulas of the language that are always true for a given semantics. And we introduce in chapter 2 the whole intuitive thing. So I now show how to define what you know already, tautologies, 0, 1, truth, false, etc. for classical formulas, how you define all this semantics as this kind of assignment, how you define the notion of tautology in a formal way. Also, in classical semantics, we assume that we consider only two logical values, and also that classical semantics connectives are extensional, so we generalize that definition of classical extensionality to the class of semantics which we call extensional semantics. And also, as you saw from the examples of languages, we can have the statement, I believe that is possible, which gives us other type of connective, and they are propositional connective, but they are not extensional. And non-extensional connectives do not play a role in mathematics, in the classical mathematics. And they are not discussed in classical logic. So intuitively, what is extensional connective? The extensional connective are defined intuitively as such that logical value of the formulas formed by the means of those connectives and certain given formulas depend only on logical values of the given formulas, how you build your formula you want to evaluate. So what does it mean? What does it mean formally? If you have language with unary and binary connectives, and then you have certain set non-empty set of logical values, can be 2, 3, infinitely many, and you have unary connective. The unary connective is a function from logical values to logical values, and binary connective is a function which takes two logical values and return one logical value, and that's how you were taught and how we defined our classical connectives. For example, you define negation, true, false, false, true, and we define, for example, disjunction, true, false, true, false, false is false, and true everywhere, right? So that's how we define what does it mean that negation is a function which takes two logical values and returns also two logical values. And the formula for the function is negation of t equal f and negation of f equal t. This is function, and this is our formula for the function. And for what is our disjunction is takes tf two values, because you have a formula a, b, right? So this is your disjunction. So it takes Cartesian product tf and returns one element. So it's two argument function. And this you read t disjunction of t equals t. Disjunction of tf equal t, etc. And we write as a function, we write that instead of tf, we put this disjunction in between. And this is t, in the same way that addition is a function, for example, natural numbers into natural numbers, and addition of two numbers, for example, gives you 2 plus 3 equals 5. So you write, instead of writing all the time that this is a function which takes two numbers and returns 2 and 3, you write 2 plus 3, and you write the plus in between. So that is the same type of notation. I just want to remind that. And so extensional semantics is when connectives are just the function of logical values. So it's very simple. And semantics with the set of m logical values is called m-valued extensional, and classical semantics is a special case of two-valued extensional semantics. And we can have, we did it all the possible numbers of two-valued connectives and so on. The next step, we want to define formally what is a tautology under given semantics. So we assume that these logical values, right, because our classical tautology, how you know, tautology is a formula which is always true, always true. So always true, what does it mean? For all these assignments of TF, for all variables in the formula. So we want to define properly what is a tautology and the semantics. So we assume that set of logical values always has a distinguished value. We can call it T, we can call it whatever you want. We can call it a smiley face but we call it T because it is our intuitive notion of the truth. And also sometimes, like in classical logic, we have a symbol T for true and F for false, and you have many values. Sometimes you want to distinguish also like one value which is like absolute F and so on. So you can, usually we use TF for absolute 2, you can use 0, 1, etc. So when you, and we use that T, the absolute truth, to define the notion of tautology. And again, extensional semantics share not only similar patterns of defining the extensional connectives, but also the method of defining a tautology. So here are the steps. We have 1, 2, 3, 4 steps to define the tautology, and for any semantics. And then classical semantics is one example of that. So these are steps. First, we define extensional connectives. So it means that we defined all this for connectives. This connective is 2 argument, is a certain function, and you have to define that function. Whatever is the set of logical values, here is the set of 2 logical values, 3 logical values, etc. So that means we define connective. Now, we define the main component of the definition of tautology. It means a function v which assign with a formula a logical value of v. So this is called truth assignment. So we will define the second. First is connectives. And the second, which I will show the slide, v, is truth assignment, which takes variables, which is atomic formulas, and assign logical value. And then we define the notion v satisfies A. V satisfies formula A. Here you have atomic formula, and then you have to say what does V do on the whole formula. And then, so this is called V satisfy A, we're going to define. And the tautology is always like that. You say that A is tautology under semantics M, if and only if all possible truth assignments satisfy the formula. And also, we use like another way of saying V satisfy a formula is also you use the word V is a model of the formula. So satisfies, V satisfy, V is a model for A, and this is a notation. So that is interchangeable, and we use a lot of, we often talk about the model. And that V satisfies a model is true for any propositional extensional semantics, and in particular in M-evaluate extensional semantics. And of course, the notion of satisfaction and model is not interchangeable in predicate logic, and things are a little bit more complex, and we'll do it in proper time. Chapter 6. So now 4 steps. Definition. A formal extensional semantics is if I give you a language and ask you to define a semantics, extensional semantics for this language, you have steps. Define the set of logical connective, and you must distinguish the value t. We defined all connectives to be extensional. What does it mean? All connectives are function, right? All connectives are logical value times logical value into logical value for 2 arguments, and for 1 argument is a function logical value into logical value. So that is a definition, depending how you define those functions. If you have a function which maps natural numbers into natural numbers, it just says the function maps, and now you can say, for example, fn equal n plus 1 is 1 function, but you can also write another formula, another function movie n square. So this is just that I have a function, and then you have to define the function. Usually you define by certain formulas or certain properties and so on. So, and the next step, we define the truth assignment. And truth assignment is always variables into logical value. And now we have also truth assignment and extension. It means you have to define what this truth assignment does on, because here you have only VA for atomic formula, what it does for any formula. And then we define the notion satisfaction, model, contramodel, and tautology. And when you go through all these 4 steps, you have defined a semantics. And of course, what differs one semantics of the other is the choice of logical values, definition of connectives, but you have always the same way you define what is, for extension of semantics, what is a model, what is satisfaction, what is the extension, and so on. So, and now we have variable assignment, which I already said, definition of variable assignment. M is the set of logical values of the semantics M. The truth assignment is always a function from variables to through the set logical values. Next step we have, because here you see I kept this, I already was preparing you to that the truth assignment is, see, truth assignment is for any variable. So for any atomic, I know what is VA, for example, true, VB equal F, and Vx equal true for all x in variables different than AB. Here I gave you a truth assignment for each variable. This is one truth assignment. But now I have a formula A or not B, and what is the logical value of this? That it doesn't tell you. You need to connect it with how you define the connectives. So that is called extensions. You see, we have variables, and here you have the set of formulas, and I have a function V which takes all those variables and maps it into true, false. Now I want to say, this is my V, what this function, I want to extend this function to a bigger domain. I want to now, and this is called extension, and we call it V star. I want to extend it to the set of all formulas, to a bigger set. So I know what's happening here, and I want to extend it formally to the whole. And how you do it? First, what is happening here, you have VA equal V star, and this is called, the extension is called V star, is VA for A in variables. And now V star of, I have one argument connective. A now is any formula, so you do it recursively. V star is star connective on V star A, because I already defined that connective. And at the same, V star of A, B, this is your formula, and I take V star of A, which I already evaluated, V star of B, and I use the definition of that connective. This is your connective, which is logical value times logical value into logical value. This is extensional, so how this connective acts on the values which I already evaluated for the formulas A and B, and we write it like with plus, we write it that this is V star of A union V star of B, and that can be any two-argument connective. So this is any two-argument connective, you have, it's like that. The V star of formula, which is a formula of A connective B, is how this connective is defined on values which already were defined for A and B. And this is called extension. And then we say that V satisfies M satisfies a formula if and only if those on the formula V star evaluates to V, and we write it like that, and we say that the V is a model. And of course, we have does not satisfy. It means it's not T. And we say that formula is tautology if and only if V satisfies under semantics M formula M for all possible truth assignment, and we denoted tautology under formula A. Now, tautology notation, we use tautology A notation. A is a tautology. This is a symbol only for classical semantics. And for other semantics, we put M here. So it says A is a tautology under semantics M, because it's a different than classical. We use only that symbol for classical tautology. And then we can have the set MT is the set of all tautologies under the given semantics. And of course, when we develop logic by defining semantics, we want semantics to be such that the set of tautologies is non-empty. So we say that semantics is well defined when we define all these functions and everything satisfaction in such a way that there is at least one tautology. And you will see that one of the three evaluate logics which we will study, defined by Kleene, which is Kleene from Kleene star, one of the biggest logicians, have the set of tautologies empty. Still, it's called Kleene logic, but it's because it's a special logic, but it's not really a well-defined semantics in our sense. And in the next steps of definition, we establish, we discuss the following cases. In set 3, 4, 5, we do the classical. So you have a nice example. We will define the tautology classical. They will talk about consistency, independence, equivalence of languages. Now, we give some examples of many-valued semantics. We study three-valued semantics. Some of them are all of them are historically very important. And they are a nice tool for examples. 4-valued semantics, 5, you can define your own semantics. Now you know how to do, and then you can see if your formula is true in one semantic, it's not true in the other. And then we generalize that definition of consistency, independence into this is for classical, and we show in how you can define it for any. Extensional semantics. Many valued semantics have their beginning in the work of Łukasiewicz. You know why you have the notion of Polish notation? Because he invented a notation, propositional notation without parentheses. And his name was Łukasiewicz, so it's called, Polish. So that's why it's Polish notation. So he was first to define a three-valued extensional semantics for our normal language and call it three-valued logic for short. So other logic, the other logic defined by the extensional semantics follows, and there is the whole field of. So in particular, I will talk soon about that historical Łukasiewicz three-valued logic, which people still use Łukasiewicz many-valued logic, so it exists as applicational. And in particular, we'll present hating three-valued semantics, which is, again, important because it has connection with intuitionistic logic and some modal logics. And for example, challenge exercise, define your own propositional semantics for that language. Language does not need to include all standard connectives. You define your own connectives, describe intuitive meaning of new connectives, give some motivation because you need to give motivation, define formally your own extensional semantics for your language, and go through carefully for the steps 1, 4. So now we go classical semantics, an example what we're talking about. And we have classical propositional connectives. All of them are extensional. And as I said, that believe, possible, certainly are not extensional. So we'll talk about non-extensional models later. And so I repeated the definition of the extensional semantics, and we apply that definition now to the classical semantics. So step 1, we define the language of logic and the set of logical values. Set of logical values, classical, is T and F. And T stands for truth and should be boldface for falsehood as the distinguished values. And now definition of extensional connective is a function. So our negation classical is defined as a function which is defined by this formula. And conjunction is another function which takes two logical values and return 1, and we write it instead of conjunction on TT, we write T, and T is T, and here is your formula. You don't write plus 1 plus 1 plus 1, 2, you write 1 plus 2, so we use that notation. Disjunction, again, this is your disjunction is a function which is defined. This function is defined in such a way. And implication is another function, and we discussed already chapter 2, motivation for those definitions and so on. Now we just do the formal, we don't discuss the motivation anymore because we already agreed at that definition of implication. Equivalence is again another function which is defined by such formula. And of course, because there are, as for any functions in finite sets, we can write it, if the set is 2 argument, you can write it in the form, this we can write it in the form of tables, and these are called truth tables for connectives. Right? So instead of writing this, this is exactly the same definition, and we use that definition as we do for any operations in finite sets. If you have any number of sets, you write the operation in finite sets as such a table. So they are called connected truth tables, and you know them. Special properties, classical semantics, a special one. It has a very specific property, which is called definability of connectives and functional dependency. We also discuss it intuitively, not that much, in chapter 2. So here is a proper definition of what does it mean that one connected is definable in the terms of others. What does it mean? That is a composition of those other functions. So it means you say that implication is definable in terms of disjunction and conjunction if it can be written as a composition of a conjunction and disjunction. And here is in general, what does it mean, a composition, a function, and so on. And here is your operation is a composition of function, disjunction, and negation, which we write instead. This is like normal composition of function. Fx equals sinus x plus 1. So here implication is not x or y for all x, y in our domain. And then you verify if really it's true. On this side you have, on this side you have. Yes, it means that those two functions are the same. So that justifies that the implication is defined in terms of disjunction and then exercises. Find the formulas defining conjunction if and only if in terms of disjunction. Find the formulas defining those connectives in terms and so on. So these are called definability of connectives, and they correspond to the proper tautologies and so on. Good exercises to do it. And then also there are very important two other important connectives. One is Scheffer alternative negation, which is defined like that, and Łukasiewicz joint negation, which is defined like that, and show that Scheffer negation defines all classical connectives. The same happens for the Łukasiewicz. So any connective can be expressed as a composition of only this one, and that is, I just said, this is difficult. Show that the two binary connectives, this and that, are each of them define all classical connectives, whether unary or binary. And and also we talk about the functional dependency of connectives. So, and in classical case, if you have the set of connectives of those languages is functional dependent, because we can express one with the terms of the other. You can express all other connectives with terms of the others. So now the second step is the truth assignment, which I am going to write again on my blackboard. V, which, because we already discussed it, variables always is set of logical values. So now it's only set of logical values, it's only 2. So this is truth assignment. And now we have to define extension to the set of formulas as we did before. So you have V and extension to the set of formulas. So truth assignment is any function from variables so this defined on atomic formulas, and we extend it to the set of all formulas in a natural way. It means on variables are the same as I erased it from the blackboard, and now you define that V star of negation is, here I put in red to show you that those red are defined by your connective truth tables. So we use the same symbols because we know that they mean different things, right? Here is a function on two value of truth and false, and here is just a formula value of formula. And also we write, as we said, with plus instead of writing plus x y, we write x plus y. So plus 1, 3. Instead of writing this is 4, oh, I still can count. That would be 1 plus 3 equals 4. We put the connective in between because it's, so that we write it like that. I put it in red just to remind you that this is connectives, and that is how you define those. And these values are defined by your connective truth tables. For example, when you look at this formula, and I have variable assignment which put A into T, B into F, and so we don't specify truth assignment such that truth assignment is always all variables. But when you look at this formula, it doesn't matter what happens there. So I say, consider truth assignments such that there's infinitely many of them, but I am interested only what's happening on NB. And then V star, you do recursive definition, all in red. And finally, you evaluate that. You see at the end here, when you are here, V star of A is VA. So that would be T. And VB was T. And VA was T. And now you see this is all algebra of connectives. So you have F. But this is how the definition works. But I let you use a shorthand notation. It means the shorthand notation, you know that A is T. You know that B is F. That I put immediately the connective. And then and now I know that T implies F is F, negation of T is F, so, and then F or F is F, and that is, all this is a formal, your shorthand notation. You are right to write the shorthand notation if I ask you to write shorthand notation, but you need to have things defined properly if you want to prove things about it. So, and then we do normal stuff. We say that V satisfies the formula if V star is T, does not satisfy, which is not T. Not T, not satisfy is not T, but in classical semantics, you have two-valued semantics. V is not T, it means V is false. So you can just write that V falsifies if it's F. If you have many values, it might not be false. It can be any other value. So, and then it's simple examples and so on. And also what I say, if I say that you can use shorthand notation, you can, here you have TFF, and then you evaluate shorthand notation to have that V satisfies that formula. And again, this is not only one V. This is V defined only on those variables, and you extend it really to infinitely many ways. And here is an example that you can have another variable assignment which says T and B and C the same, and then I put for other formulas, for example, F, and here, of course, this would satisfy that formula, and then I can extend it in different way, so that would also satisfy that formula. So, so now there would be a question, how many V, if you have a V which satisfies formula, how many V would satisfy a formula? And now we have also the language of model, V which satisfies called model or contramodel. And tautology it means that V star A is T for all V, or you can say that all V's are model for, you see, all V for all V, V is a model of A. So it means because V satisfies L for all models, you can drop the V, and that's why you get that, that symbol for tautology. And so now, tautology verification method. So let's think a second, because once you have this definition, tautology is for all possible V. But how many are this V? And I just show you that how many is all possible truth assignment. So when you have a set, we write this as the cardinality. In a case, it's the number of elements, and infinite, and their names. Cardinality of countably infinite is called Aleph 0. So for any countably infinite set, and cardinality of real numbers is called continuum. So cardinality of X is continuum. if has the same cardinality f as the real numbers. And now you have counting function theorem for any sets. If you have set x and y, especially when set is countably infinite and y is finite, you have n to the power aleph 0, it equals c, so it all possible functions which map the set y in x into y. So it means in this case, y is just 2, so you have 2 to the power aleph 0 continuum, so you have uncountably many v's. So for any v, it says tautologies, for any v, you say uncountable, as many as real numbers, those v's. So how you really know that something is tautology if you have to evaluate all possible v's? Fortunately, we don't need to evaluate all possible v's. So we've called variable a is all set of all variables which appear in A, and really the VA such that maps variables in A into TF are called the restriction of V to the formula A. And you show that you have restricted model that V satisfies A if and only if that restriction satisfies A. So it means that you can count only the restricted model. So for example, here you have formula, you have variables, 3 variables. So you can count how many are those functions which takes 3-element set into 2-element set. You have counting finite function theorem that for finite sets, if n has n elements, b has n elements, there is m to the power n possible functions. So if you have here, the functions are from 1 to 3 to 2, because you have 2 logical values, would be 2 to the power 8 truth assignment. And so in general, you have counting restricted truths that for any A, they are 2 to the power the number of variables in A of restricted models. And that's how you do check if something is a tautology. You check only all restricted models, right? You have 8 restricted models. And then you have computation, because you have to compute that value for this V on this formula. You get T everywhere, so you have all restricted contramodel, and you show that A is a tautology. And in general, you have, of course, that V is tautology if and only if VA satisfies A for all restricted model. So you have the decidability theorem that any formula, one has to examine only 2 to the power the number of variables in formula. It means you can evaluate only restricted models for A to evaluate, so to decide whether A is a tautology or is not a tautology. So the notion of classical tautology is decidable. And so we proved it, which you know because you've been doing. And of course, you can do it what's called truth table method. So it means you evaluate all of them. It's a lot of evaluation. So it means this is called truth table method. It means consists of examination the formula, all possible restricted. If we find truth assignment which evaluates to F, we have not tautology, otherwise continue, and then just find a number of them, so you always find them. And that's how you evaluate. And this is a proper way of building your truth tables. Right? This evaluation is the algebra of connectives, and that's what you get. But also, it's a lot of evaluation. If you have a lot of 200 variables, you have 2 to the power 200. You can write a program, but still it's a big number. So we often use, and almost all tautologies we prove is by using proof by contradiction method. It means in order to verify tautology A, we work backward, trying to find the truth assignment which makes formula A false. If we find one, it means I have a contramodel. If we prove that it's impossible, we get contradiction. Impossible, it means we get a contradiction. So it means we know that formula is a tautology. For example, you have a formula. We want to find which is tautology. So assume that it's not. So it means we evaluate in F. And I let you use shorthand notation. So this is F. What does it mean? Main connective is implication. Implication is false only if and only if this is true and this is false. Now you analyze this step. If I know this is true, I get that A or B is false if and only if true and B is false. It happens only if and only if B. This is impossible because you have T here for any B, so you get a contradiction, so you prove the tautology. But also, when you look that you can do the same reasoning for any formula A. Now, just to remember, now and forever, A, B, C variables A, B, C are any formulas. So these are, that's why we use a different. If I say here capital A, it means that A can be any formula. For example, A can be this. And you can see that this is a tautology and this is a tautology because this formula is built as this is A. My main connective is this, right? So this is formula A. That is repeated here. And B is not D. And then it's another. This is A. This is repeated here. And D is there. So this is, I want, this is A, this is A up here, and this is B is this. They are all particular substitution of this formula. This is substitution, this is general schema. So if you have a formula like that, you can like see, oh, I don't need to go through all this because I know that this is substitution of the formula. It has a schema A implies B. A implies A or B. And then you have substitution method, which allows us obtain new tautology from already proven tautologies. And this is, we have a theorem which says that the correctness theorem that of any formula which has certain variables and other formulas, if A is tautology and B is a formula which gets substitution for each variable another formula, B is also tautology. And there is a proof. And so the correctness theorem establishes validity of use of substitution method. Good, and also you have generalization method, which is that a given formula is a particular case of some much simpler, more general formula B. And here is your substitution method. You have more complex, and this is this formula is substitution of that. So this is tautology because this is a tautology. Now you have a set of tautologies, fat T, and we use it for classical tautology, remember? And then we introduce also the notion of contradiction. Contradiction is the inverse of tautology. We say A is a contradiction if and only if for all variable truth assignment, V does not satisfy A, and you have the of course, in all our possible formulas, this is a tautology, this is a contradiction, and this is nature. So you have contradiction, you have tautologies, you have contradictions, and you have infinitely many formulas which are nature. And here is like simple, for classical logic, and you can see if you have another semantics, does it hold for other semantics, for which semantics similar theorem holds the. So the next important notion is the models for the set of formulas. And that we, so we say that the truth assignment, simple definition, is model for a set formulas. You have any set of formulas of our language. And that now is the language set of formulas. And we say that V is a model for the set of formulas. V is a model of the set of formulas if and only if V is a model for each single formula of S. So it means V satisfies all formulas. And of course, contramodel of non-empty set if and only if V does not satisfy A for at least one formula, for some formula A. And of course, you can have S is finite. If it's finite subset, you have also finite number of variables. So the variables in S is finite. So we can go to restricted models, and you have decidability of having decidability of S having a model or not for finite S. And we talk about the restricted, the counter model for set is when you take the variables appearing in S, so it's restricted counter model. And for example, here. Now, I'm going to do it to make it simple. You have a little set. And let's take a set S of formulas, A and not B, C not B, and does it has a model? What does it has a model? I want a restricted model. I said I give you, and then I evaluate. Now let's see. I want to set does S have a model. So what does it mean? I have to put all pieces of formula. Is it possible to put all in T? Right? So if it existed, I would have to have A must be T, C must be T, not B T. It means B must be F. So I have this, and now I check what happens with this formula. You have T and not BT equal T, yes. And you can see, yes, it has a model, and also I prove that is only one model. One model. Because here's one, here's one, here's one, and it fits this one. So you have only one model, A equal T, B equal F, C equal T, restricted. Right? So you have finite. So that is the model of the set of formulas, and you can, that's how you use the shorthand notation. Of course, what happens, can we have infinite set which has a model? Of course, the set of all tautology. Any V is a model of tautology. So if you have T, S equal T, set of all tautologies, it is infinite and has a model, right? So, but can you have a set, infinite set, which does not have a model? Again, you can have a trivial example. It's very important to have a trivial example. Infinite set, you can have set of all contradictions. does not have a model, because none of contradict, but so, and again, I give an example of infinite set, which is not a tautology that has a model. Give an example of infinite set, which is disjoint with tautologies. That is trivial. Not equal tautology. You can take one tautology out, and you have set which is infinite, and it's not the same as a tautology. But then it's a little bit more difficult. Give an example of infinite set which is disjoint with tautology and has a model, and so on. So this is just have fun. Now, this is important notion of consistency. We say that the set S is consistent. S is a subset of formula, consistent if and only if has a model. So it means we prove that this set is consistent, right? Otherwise, it's inconsistent. So otherwise, inconsistent, consistent S is if do not have a model, does not have a model. And again, give an example of consistent set. We already has a model. We already give this which is consistent. I just reworded the questions. These questions has a model, consistent. Consistent. Does not have a model, inconsistent. Has a model, consistent. So it's just wording the same question in different way. Now, that is very important notion, because this notion of sentences which are independent of a set are used to prove in, the notion of a formula independent of the set is used in the proof of Gödel incompleteness theorems, which is the goal of the whole classical logic. So we say that the formula is independent from the set if you can have two models. You can have V1 model of G where you add formula, and V2 model of G, and you get negation. So you add formula to the set or negation, it means these are both consistent. Adding formula to the set or adding negation, you get consistent set. So that's why formulas like that are called independent of the set. So A is independent. Independent. So we proved that this set was consistent, and we found that that one had only one model. And here I was like writing with all these V's. So, and show that this formula is independent of the set. You know that that model you have, so you have to find two models. One that would be a model for G, which was A equal F, B equal T, and V1 has to be a model for G. So you know that for A and B, because that was the only model, must be like that, and formula has a C. Let's take as V, that was our model for G, and we put C, T, And let's take another v when we put cf, and we get that v1 satisfies this and vy satisfies negation. So we prove that A is independent. And then, for example, this is a formula. Such formula is not independent because it's impossible to find, and so on. And then again, you have different example. Given a set, find the formula which is independent, and you play. That's a lot of nice challenge problem. Find an infinite number of formulas that is independent on our G. Not one, two, infinite number. And okay, this is my solution, but it's very simple because I like simple solutions. So we just proved that that A is F, B is T is the only model restricted to variables A and B. So let's take set F0 of formulas which are variables which exclude A, B, and all atomic formula. So if C belongs to this, we put C. You see our AB, we put the model for G, and V1 would be the model for G, and I put for C, another C is true, so that would be a model for that formula for G union C, and if I put another one, F would be the model for this, and you have infinite number of formulas which are independent, each variable different than A, B is independent of C, D. That's a very nice, but you can have more complicated. So now is classical tautologies. So I'm not going to go too much into tautologies because we already discussed it in the previous chapter. But I want to discuss about logical equivalences. Here is some tautologies, which are very important tautologies. So I'm listing you some tautologies which are important to remember and will be used. Disjunction, conjunction tautologies, you have contraposition laws, these are tautologies with if and only if. So these are double negation, contraposition laws, so these are all classical tautologies. So when you have tautologies which deal with if and only if, we introduce the notion, which is a very useful notion, which is the notion that two formulas are logically equivalent, and we write A logically equivalent to B. This is not a symbol, it is not a connective. It is our meta-language symbol which says A is logically equivalent to B. You don't like to write equal because we talk about logical equivalence. So, and we defined it that A is logically equivalent V if the logical values are the same for all possible V. So of course you have immediately that A is logically equivalent B if and only if A if and only if B is a tautology. So in a sense, that represents this type of tautology. Why we do it? So for example, the contraposition law, we can write as logical equivalence. Other contraposition is as logical equivalence. Double negation, we write. So all tautologies which we had for if and only if connective, we can replace this and write that as logical equivalence. Why we do it? Because we can just use that notion logical equivalence. We can write something like that. A, not A implies B is logically equivalent, not B, not A. Now not A is A, so I can have new contraposition law, etc. You can treat this as equality, which you cannot write this for a if and only if connective. So it's very useful. And of course you have substitution theorem, because we here, what I did, right? I use the law, and now I know that double negation A is logically equivalent to A, so I can replace this by logically equivalent formula. So you can have substitution theorem that if you substitute if you substitute logically equivalent, what you started with is logically equivalent, and you just play with it. So that substitution theorem shows you that you can, if you want to play with, if you evaluate logical equivalency, you see that is logically equivalent to this, so you can substitute this by that, and you have everything is logically equivalent. So this is, you have to state it, and you have to obviously prove it, which is pretty obvious proof. So now we have certain important logical equivalences which are called definability of connectives. Like, for example, you can write that A implies B for any formulas is logically equivalent to not A or B. And then you can transform by substitution theorem one formulas into the others. So that was definability of implication, which is that logical equivalence, which corresponds to that tautology. And all the connectives which are logically equivalent, you can transform. When you have logical equivalences, you can transform one kind of formula into other formulas. For example, if I have such a formula, and I know definability of implication by not A or B, so I can transform this formula into, like, for example, here what I do, this is your A, so you have not A or B. So now I can again I can replace this implication by not C or B, and B it means not B. So what I had a formula with implication, and I got rid of implication. And now I have another important definability. It means that I can define disjunction in terms of negation and implication. So it means that anywhere I have disjunction, I can replace disjunction by implication and negation. So, for example, I have a formula like this, and I want to get rid of disjunction. I can replace this disjunction, not A and B, and I get a formula which does not have disjunction. It means here, when you look at this formula, we have a language which had disjunction, and I can change this language which does not have disjunction but have implication instead. So we have the notion of equivalence of languages. We say that two languages are logically equivalent if and only if that they have some connectives. Any formula from the first, there is a formula from the second which is logically equivalent, and vice versa. Any formula from here, you can find a formula of that language which is logically equivalent. So, for example, prove that language which has negation and disjunction is logically equivalent to language with negation and implication. What does it mean? That you have to replace in any formula disjunction by implication, disjunction by implication. You have logical equivalence, and also you can replace from this side implication by disjunction. So in both ways. You have any formula of this language can be transformed into the formula of that language by this, and any formula of this language can be transformed into formula of this language by this, because you get rid of implication introducing disjunction. And so, of course, you can have another. You have definability conjunction in terms of implication and implication in terms of conjunction. And substitution theorem, you can have that. You can do the same for conjunction. Conjunction by this, you can replace by implication, and you are here. And here, implication here, you can replace by this. You are in this language. And of course, you have substitution that you do it each time by substitutions. And prove that this is logically equivalent. You have to express conjunction in terms of disjunction and disjunction in terms of conjunction. You have, this is all definability of connectives. And you have some frequently used logical equivalences and more. The Morgan law, negation of implication, and some exercises. You have a concrete formula of the language and find a logically equivalent formula of another language. You take this, and now you want to replace in a proper way. So it means wherever you have conjunction, you have to replace by disjunction. And here you have the replacement. And then again, I have conjunction. I replace by disjunction. So I get a formula which is logically equivalent from another language. And, for example, prove by transformation using the proper logical equivalences that such equivalence holds. You start on one side by definition of if and only if is implication on both sides. By De Morgan law, you do this. By negation of implication, you get that, and then you get. So this is a lot of that's why you have to know your tautologies. You have to know your logical equivalences. So what I'm saying that classical logic is very beautiful because we already know it, but it's very regular. So let's see now what's happening when we move out of realm of classical logic. And there's many valuate logic. Okay, the study of many valuate logic was started by Łukasiewicz, as I said, and he was the first. We defined a little three-valuate logic. And then, it means we define the logic by giving three-valuate semantics. It's called logic defined semantically. And of course, if you define certain semantics for a language, you can just define those connectives by whatever you want the functions, but you have to convince people that it makes sense. So it means you have to give some motivation to that semantics. So when you create a new logic, you can do it on the given language is based on three principles. You define the semantics, you can define the axiomatic proof system, and you can prove completeness theorem if you have both, and that you have full-fledged logic. If you have only semantics for the language, it is your logic defined semantically. If you have only the proof system, it is your logic defined syntactically. And if you prove completeness, connection, you have the full-fledged logic. So we define now, which they call many valuate logics, but they are really, because they are called logics, but they are logics defined semantically. So we give semantics for some historically important three-valuate logic defined semantically. And so the language is the same, but except for Borchvar, which would have another connective. And three-valued semantics have three logical values, and we denote the third logical value by unknown. This is, you can write 1, 2, 3, but and in Borchvar logic you have M. And that third logical value denotes unknown, uncertain, undefined, whatever the symbol is this. And the way different semantics or different motivation explain why you define, because this is extensional logic, why that value, your connective are defined in such a way because you have motivation for that. So it can be incomplete information, inconsistent information, undefined, unknown, and also we say that's logic defined semantically. So, and we have some assumptions. First, we assume that it's easy, it's nice to have. You don't need to have always, but we assume in our framework that they are ordered. So there's order. F is less than unknown, less than T, and the same for M. And the T is designated value within used to define satisfiability and tautology. And now we have our 4 steps. I'm not going to repeat to define semantics. And also, as I said, if to define semantics, you have to explain, you have to convince people that it makes sense. So Łukasiewicz developed his semantics, or called logic, to deal with contingent statements. So he said contingent statements are not just neither true nor false, but indeterminate in some metaphysical sense. It is not only that we do not know their truth values, but rather they do not possess one. And very nice. So following that, he defined negation, like a negation of unknown is unknown because it does not possess value, it still does not, if you negate, it does not possess. Conjunction is minimum, and we can write here minimum xy because they are ordered. So you know that is your formula for conjunction. X and y is minimum, so you can, because we assume that they are ordered. Disjunction is maximum. When you look at our truth tables for classical logic, it's the same conjunction and disjunction if you say that false is less than truth. And implication. And here's the formula for implication, and I'm going to write it because it's a very, so you have x, y is min, x, y, x, y is max, x, y, and of course x, y are now true, unknown, false, and false is less unknown T, so that's why you have max. And negation, and negation, we assume that negation of unknown is unknown, and on T and F, negation T is F is a classical, and negation F is T. And now the implication X implies, this is connectives, this is definition of connective. X implies Y equal not X or Y if X greater than Y, perfect formula, T otherwise. And this is nice function, right? The implication is a function which takes 2 values, and this is your formula. Of course, if you can write the function is implication on 2 values, and we write it like that. That's why we write it like that. So, of course, what you do, you write it in nice tables using those formulas, right? So you have f, and f is minimum, like this, and this is minimum, t and t, f, and this and f is minimum, etc. This and this minimum is this. So you have you write those as a truth tables, but this is your formula. And always, once you have unfinite sets, you have formula, you can write those truth tables. Did I? In an implication, I wrote all of them. But you don't need, you have that, you can evaluate it. And now you do the normal step truths. Your truth assignment now would be in 3 values. And then you do extension exactly the same. You see, with and satisfaction is exactly the same. Satisfy if it's t, and does not satisfy is not equal t. That's why we, from the beginning, wrote, because now not equal t can be false or unknown. And model is called now L model. Any v that v satisfies in the semantic cell. Contra model is v does not satisfy semantic cell. Tautology, L tautology is v, all v are models, so it's L models, so you have exactly the same pattern. And now, okay, so now I have all the, I defined, I have all the LT, L tautology. L for Lukasiewicz. And so now, did I get something different? Did I get something different from classical? I have some of the functions, I have more values, but did I have something different? So it means, are the set of tautologies of classical logic and that semantics different? Oh, yes. And for example, this, yes, but for example, not A or A, excluded middle does not call in Lukasiewicz logic. Why? Because if you put A unknown, here is written V star very nicely. This is a shorthand, not unknown or unknown is unknown or unknown. So this is a contramodel. So Lukasiewicz is different than classical. So we got something different than classical logic. Now, do they have something in common? This is natural way, because if you create a new logic, you always have to say how it relates to classical logic, which is the relationship between classical and that new L tautologies. And of course, if you restrict the function of connectives, you see when you have those functions, if you restrict them to only to t and f, you get exactly classical functions. So LT, the tautology, are included, not equal the classical tautologies. And that's proof. And then you can, for example, one nice exercise. So we know that we have a logic which is all tautology are, all tautologies are classical, but not all classical tautologies. So we have a real, and of course it's non-empty. I didn't show you that's non-empty. A implies A is a tautology. And so, and then you can do some exercises. Like for example, we know that we have some V which evaluates that formula into unknown. Use this information to evaluate the value of another formula. And you can use shortcut notation. So what does it mean? I know that, but the main connective was implication. And when you look at the definition of implication, or I'm not going to rewrite, but you can write those connective truth table for implication. If you write this connective truth table for implication, you can see that implication is unknown in two cases. So it means when this is unknown and this is false, or the second case is this, and you consider one case, and it happens only this. So we get, you get that from this case, you have that A is unknown and B is unknown, and then you can evaluate the formula, which you already have only A and B. In the second case, you evaluate as T, so both cases give you a model for that formula. And Łukasiewicz was born in Lwów. That was historically Polish city, and that time was capital of Austria, Galicia, and now it's in Lithuania, and died in Dublin. And so the second, which I want still discuss, is the hating semantics. This is important. Łukasiewicz is important because he was first to invent it, that you can have more values that we have logic which has more values. Hating is very important. It's called hating three-valued logic because the connective are defined as operation in our set in such a way that they form three-element pseudo-Boolean algebras, and pseudo-Boolean algebra were created by Makisen and Tarski in 1948 to provide semantics for intuitionistic logic. So that's why, and pseudo-Boolean algebra is also called hating algebra, to honor hating, because hating was a person who gave first axiomatization of intuitionistic logic. And intuitionistic logic was defined by Brouwer and his school in 1900s as a proof system. Hating provided the first axiomatization. And Makisen Tarski invented the semantics and proved completeness of hating axiomatization under his pseudo-Boolean algebra semantics. We'll discuss it in algebraic models later. So, and we say that the formula is intuitionistic tautology if and only if it's true in all pseudo-Boolean algebra. So there is infinitely many in them, and this is a very complex creatures, but we prove that the operation of hating connectives form a three-element Boolean algebra, pseudo-Boolean algebra. So if A is intuitionistic tautology, is also hating, our hating three-valued hating semantics tautology. So if it's not three-valued hating tautology, so it's not intuitionistic tautology. Just to remind you that A implies B is logically equivalent, not B implies not A. So that we use this to say if not three-valued hating, so it's not intuitionistic tautology. It means those little algebra, the little semantics gives us this chance on finding that a formula is not intuitionistic tautology, because if it's not hating, which you can check into those three values as we did classical, you could know for sure that it's not intuitionistic tautology, but not vice versa, of course. So, and now again, you have another semantics or another logic defined semantically. So you ask how it relates to classical, how it relates to already Łukasiewicz, and of course we have that the relationship between intuitionistic and hating are that any intuitionistic is a hating tautology. So if it's not hating, that is not intuitionistic, we already show. Now, the other type of semantics for intuitionistic logic were defined by Kripke in '64. They are called Kripke models. And they are equivalent to pseudo-Boolean algebras, but we don't. And also Kripke model covers modal logics and so on. So, H semantics, you have implication is different. You can see that these are the same. Now, these are the same. And implication now in hating, and I want to write it. See, now implication, hating implication is T is T if now X less equal Y and this Y otherwise. And negation is negation of X is X implies F. Of course, X, Y are element of T, your logical value. This is our definition of connectives. Definition of connectives. T unknown F. So, different implication, different formula for implication. And now, of course, you can write implication truth table and negation because conjunction and disjunction is maximum, so you don't need to. And you can see that implication is unknown only in one place and negation is. And so now we ask already, you have hating, you have normal tautology and L tautology. How is a relationship? They're all different because, for example, we have that A or not A is not hating tautology and is classical tautology. And you have that hating is different than L because if you have A and B is unknown and you have this is not hating and this is Lukasiewicz, this is classic Lukasiewicz tautology. So, and then you can also hating when you look carefully at the definition, you have the same properties we had for Lukasiewicz, that when you restrict only to values of T and F, that you get classical connectives. So Lukasiewicz was a subset of classical, and hating is also a subset of classical tautologies. And Kleene, Kleene had a nice example. I'll read you just example. Motivation. So he wanted to model a situation where the third logical value intuitively represents undecided or state of partial ignorance. And a sentence is assigned unknown in case it is not known to be either true or false, right? Ignorance, I don't know if it's true or false. So it's pretty, so for example, he gave an example. Imagine a detective trying to solve a murder. He might conjecture that Jones killed the victim. He cannot at present assign the truth value to his conjecture, so we assign unknown. But it is certainly either true or false, so the unknown represents ignorance rather than unknown. That is motivation. And doing so, he kept negation like Lukasiewicz. You see, this is like Lukasiewicz. This is the hating negation was different. This is classical, max and min, and you see, say implication is like classical, right? This is the formula for classical implication. So you write the truth table for Kleene implication. And then you say, ask, okay, Kleene, you have this, this is Łukasiewicz, this is not Kleene, you have that the Kleene tautology are different than classical, different than Łukasiewicz, and so on. And you have Kleene, because when you restrict again to TF, you get Kleene, so it's the same like in previous cases, it's a subset. You have all these nice properties, and and also, so for all three of them, you have the decidability, because for all of them, you can have the same, that A is tautology at one of those semantics, if and only if you can look only at restricted models. That theorem holds like the same way as it holds for classical. So you have, again, the decidability for all of them, because you have to, now you have three logical values. So you have variables in formula A. For any formula for all those semantics, you have to examine 3 to the power variable A of possible truth assignments. So it's decidable. So it's very nice. And now let's look at this. You have a classical tautology, and none of them is Kleene tautology. So then you can say, and for all of them, the A and B unknown is always a contramodel. And we generalize this example that prove by induction over the degree of formula that this, for any formula with any, whatever are the variable, that all variables are known, is a contramodel for any formula. So we prove that the set of tautologies is empty. That's why we had the definition that semantics is well defined if the set of tautologies is not empty. Nevertheless, it is respectable semantics because it's interesting. And of course, all our statements we prove are true, because the classical, the tautology is empty. So you have that LT is not empty, this is not empty, this is not empty. This is a subset of Kleene tautologies, a subset of classical tautologies. Of course, empty set is a subset of any set, and so on. So again, I just put it here that that's why we use the definition that giving a language and semantic we say is well defined. It is defined, but we don't call it well defined if they're only the set of tautologies are empty. And then we look, so the semantics LH are well defined. Kleene is semantic not well defined in our sense. And then there's Bochvar semantics, which is have another logical value, have the logical value M, and have, here is nicely because they are defined by connective truth tables. And also you have the assertion operator. And then you have the Bochvar tautologies, and then again you ask, is the semantics well defined? Yes, it is well defined because you can prove that this is tautology. And then you can see that for some type, like for example, none of this is a tautology because M is contramodel. So, and then you can prove that this is a nice three-valued logic, but an example of semantics or logic semantically defined, which has non-empty intersection with classical tautologies. So this is just, and now this is just to remember we were talking about consistency, we were talking about equivalence of languages, and that we can generalize all those notions for our any M. We generalize those notions for extensional semantics N, and we assume that because we define extensional semantics that logical values can be any set. Now we say it's finite set, just to have a similarity of generalization. And then again, we have, if we assume that we can now consider extensional semantics with finite set of logical values, so we have that decidability theorem in exactly the same way we proved it for our examples of logics. And then we have truth table model, because you have the number of logical values to the variables in the formula A. So you have the decidability theorem, and this is called truth table model because you can evaluate all those V from here. If you take one by one, if you find a contramodel, you stop, otherwise you continue, and there's a finite number of them. And for example, you have H semantics, you do the truth tables as you need. Another example, you show that this is a tautology. You have the proof by contradiction method, and you have also the substitution theorem in some way we had for the classical semantics. And then you have equivalence, right? So you can also, you see, remember we had this, you have such a formula in a logic. Is this a tautology in our L logic? But when you look closely, you say, oh, that formula is not A implies A. For A, and so now you have only to have to check this, which you do by contradiction, or you can check by truth tables and so on. So the next thing is set of formulas, and we say is M consistent, exactly the same definition. If there is a truth assignment, which is a model for all formulas. For G, it means it's model for all formulas of G. Is exactly, here you have our set still the same. Prove that it is M consistent for L, H, and K. Is it? So, and you go exactly the same. Now you have a little bit more consideration because you have one more logical values. And for example, give an example of infinite set G of formulas of the language Bachvar, which is L, H, K, and B consistent. That's a good one. That's a good one. And to give an example of two sets containing some formulas that include S connective of this language, such G1 is B consistent and GB is not B consistent, and you can have a lot of nice exercises. And of course, you have the same definition of M independent. You have a language, and now we are without and I say that formula is M independent if G and A or G or not A are consistent under the given semantics. And given a set, find the formula independent L independent of G, find formula H independent of G infinite number of L-independent formulas of G, or infinite number of H-independent, and so on. And of course, the next step would be the equivalence of languages. It means we introduce, in a similar way, the equivalence of two formulas with respect to the semantics M. And again, this is not logical equivalence. It's not logical connective. And then you can, for example, that classical logical equivalence is not Lukasiewicz logical equivalence. So I said, okay, can I still have express, because that was defined, you could replace disjunction by implication. You can do it like that in classical semantics, but not in Lukasiewicz semantics. But still, we can find that there is a contramodel, and then you have the logical equivalence of languages, which is exactly the same definition, but now everything is relative to a semantics, and proof, for example, that this language is logically equivalent to that language. It means that you can express disjunction in terms of implication, and here is our formula that A union B is logically equivalent to this, and you can check it using L semantics. And that is, I think, the end of chapter 3.